Welcome to section 2.2 set operations. Again, we are using the text Discrete Mathematics and its Applications by Kenneth H. Rosen, and this is Dr. Gilbert Eyabi. Section 2.2 Learning Objectives. Number 1, set operations. Union. A union B would be the set of all elements X such that, this line means such that, X is an element of A or X is an element of B. So A union B, the set of all X such that X is in A or X is in B. Then we would look at intersection, and A intersection B would be the set of all elements X such that X is in A and X is in B. So union is or and intersection is and. Then we will look at complementation, or the complement of A, which is written as A prime or A bar or A with a little c on top of it. And that is simply the set of all elements X such that X is not in A. Again, when we say the set of all elements X, we assume that the domain is properly defined. In this case, the universal set is properly defined. And the difference, A minus B, is the set of all elements X such that X is in A and X is not in B. And that is just A intersection B prime. When we are proving anything involving difference, we would write A minus B as A intersection B prime. It's a lot easier to deal with it in this form, because then if I say that let X be an element in A intersection B prime, then that means X is in A and X is in B prime. But X in B prime means X is not in B. Okay, we'll play with that some more when we come to proofs. Then we would look at set cardinality and some identities, and then we would conclude with proofs and membership tables. It's beautiful. Okay, let's go ahead and start with an introduction. Boolean algebra, propositional calculus, and set theory are both instances of an algebraic system called a Boolean algebra, and we shall discuss this some more in chapter 12 if we actually get there in this class. The operators in set theory are analogous to the corresponding operator in propositional calculus. As always, there must be a universal set. Now, unless we anticipate confusion, we would not talk much about the universal set. It would be clear from context. All sets are assumed to be subsets of our universal set, which is also assumed to be obvious in most cases. Okay, let's start with our learning objectives. Definition number 1, union. Let A and B be sets. The union of A and B, denoted by AUB, is the set of all elements X. Again, we could have said a set of all elements X in the universal set such that, but the universal set in this case is assumed to be obvious from context. So the set of all elements X such that X is in A or X is in B. Now, what is really important to us is how we use this in proofs. So in proofs, we would say let X be an element of A union B. What does that mean? It means X is an element of A or X is an element of B. Okay, now this is an if and only if, which means if I say that X is an element of A and X is an element in B, that means X is an element in A union B. And if I say that X is an element of A union B, it would mean that X is an element of A or X is an element of B. Okay, so it's an if and only if. I can go both directions. Master this. We would use this a lot in proofs. Now, a very simple, straightforward example. If A is a set 1, 2, 3 and B is a set 3, 4, 5, then A union B would be the set 1, 2, 3, 4, 5. Observe that there is no need to repeat 3. So it's just 1, 2, 3, 4, 5. And if this is my A and that's my B, my A union B would be the shaded region. And our universal set is U. Intersection. The intersection of two sets A intersection B, denoted as follows, is a set of all elements X such that X is in A and X is in B. Again, we would be interested in how we interpret this when we're dealing with proofs. So if I say that X is an element of A intersection B, what does that mean? It means X is an element of A and X is an element of B. And the reverse, if I say that X is an element in A and an element in B, that means X is an element of A intersection B, both directions. Okay? This is how we prove things involving intersections. Again, a minor example, that's A, that's B. The intersection would be the set of elements that are common to both A and B. And in this case, it would be this shaded region right here. And for this example, it would be the singleton 3. And if I look at these two sets, well, the intersection is empty, the empty set. Complementation. The complement of A is denoted by A bar, A prime, A with a little c. I prefer writing it as A prime, but you could use any notation. So that is simply the set of all elements X in the universal set such that X is not an element of A. Again, we're interested in proofs. How do we apply this in proofs? If I say that X is an element in A prime, that means X is not in A. And the reverse direction, if we say that X is not an element of A, it means X is in A prime, if and only if. So we would use this in proofs before we get done today. Okay, so if we look at our Venn diagram right here, the shaded region is our A complement, and this is A. Observe that A intersection A complement is the empty set. Okay, there cannot be an element in both A and A complement at the same time. Okay, now let's talk about difference. The difference of A and B, A minus B, as we mentioned before, would be the set of all elements X in the universal set such that X is in A and X is not in B. Now, some books would use but and, as a matter of fact, to have a very close relationship. So you could say that A minus B is a set of all elements X such that X is in A but X is not in B, and that would have the same meaning as the word and it is interpreted as A intersection B prime. Again, we use this a lot when we're dealing with proofs. So this is what we do. So in proofs, if I ask you to prove something involving A minus B, you would say let X be an element in A minus B. What does that mean? It means X is an element of A intersection B prime, so we convert A minus B as A intersection B prime. But what does that mean? That means X is in A and X is in B prime. What does that mean? That means X is in A and X is not in B, and so on and so forth. And we continue until we get to where we're going. Okay, so that would be A minus B. And using Venn diagrams, what that simply means is A minus B is not the same as 5 minus 4, which is 1, or 3 minus 1, which is 2. It simply means all the elements of A, and I take out all the elements of A that are also elements of B. So I'm interested in just this shaded region right here. Okay, so A minus B is a set of all elements in the universal set which are in A, but those elements are not in B. So A only. Okay, now let's talk a little bit about the cardinality of the union of two sets. And what I'll ask you to do here is to remember this formula right here. If you've taken any class in probability, you would have heard of the addition rule of probability, and it's very similar to this. The probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. And believe it or not, that holds for cardinalities also. So the cardinality of A union B, remember the cardinality is simply the number of elements of A union B. That equals the cardinality of A plus the cardinality of B minus the cardinality of A intersection B. You can decide to memorize this as the addition rule for cardinality, just like we have the addition rule for probability. And they all deal with the number Remember, probability is simply the number of outcomes that fulfill a particular event divided by the total number of outcomes. So here would be the number of elements in A union B equals the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. Okay, and we have a few examples here. I'll leave this for you to enjoy. Now let's look at some review questions. If the universal set is the set from 0 to 10 and A is the set 1 to 5, B is the set 4, 5, 6, 7, 8, find A union B, A intersection B, A complement, B complement, A minus B, B minus A, and so on and so forth. And I'm going to leave those as SIFs, simple exercise for serious students. In this case, it will be simple exercises for serious students. Okay, let's move on to symmetric differences. We didn't mention this in our learning objectives, but you may want to know a little bit about the exclusive OR. So far, OR used in this class or in general in mathematics or even everyday language is the inclusive OR. If I say that for dessert tonight, I would have a slice of pie or a scoop of ice cream. The understanding is that I would either have a slice of pie and I'm done, or I would have a scoop of ice cream and I'm done, or I could actually have both. So that's the inclusive OR. Now, what is the exclusive OR? The exclusive OR means it is either A or B, but not both. And we can use that to define what is known as the symmetric difference of A and B. The symmetric difference of A and B, A exclusive or B, is the set A minus B union B minus A. Now let's look at the Venn diagram to really explain this. So that means it's A only, B only, and there is nothing in the intersection. It cannot be A and B. A only, B only. So that is A or B, exclusive or B, the symmetric difference. Example, that's a universal set. That is A, that is B. Go ahead and compute A symmetric difference B, or A exclusive or B. That should give you 1, 2, 3, 6, 7, 8. And the details of this solution will be left as a SIFs, simple exercise for serious students. Now let's look at a bunch of set identities. The goal here is not for you to memorize these identities, but for you to try to prove as many of them as possible. And in proving them, you'd actually get to remember this if you were to see them somewhere in a test or just walking around and having fun with math. Identity laws. A union the empty set is A, and A intersection the universal set is A. Okay, this should be obvious. There is no element in the empty set, so A union the empty set is just A. A is a subset of the universal set, so A intersection the universal set is just A. Domination laws. A union the universal set is the universal set. Again, that is obvious because A is a subset of the universal set. So if I take a subset and take a union of that with the set U, it's just U. And A intersection the empty set, of course, the empty set is a subset of every set. So the empty set is a subset of A. So A intersection the empty set is just the empty set. Or you could just use the fact that there is no element in the empty set. So it doesn't matter what A is. If I intersect it with a set that has no elements, well, the result will be no elements. Idempotent laws. A union A is just A. Pretty straightforward. A intersection A is also A. Complementation. We will see this over and over again. A complement is A. When I introduce the concept of matrices, we will say A transpose is A. A inverse is A, and so on and so forth. Okay, so more set identities, commutative properties. A union B is the same as B union A. That's pretty straightforward. A intersection B is the same as B intersection A. And then we have the associative laws, which would permit us to move parentheses without changing the solution. So A union B union C, and I start off by evaluating B union C first, is the same as A union B union C, where I evaluate A union B first, and the same holds with intersection. And distributivity also holds. A intersection B union C would be the same as A intersection B union A intersection C. So I'm distributing the intersection over the union, and here I am distributing union over intersection, and the solutions would stay the same. I would need you to attempt the proofs of these two, and of course all the others. And then we have De Morgan's laws. A union B, all of that complement would be A complement intersection B complement. We've seen this before in logic. A intersection B complement equals A complement union B complement. I'll need you to prove both of these. Absorption laws. A union A intersection B equals A. Almost looks complex until you observe that A intersection B is a subset of A. So A union, a set that is a subset of A, just gives us A. Similarly, A is a subset of A union B. So if I take the intersection of A and a set where A is a subset of, that just gives me A. Okay, and some laws involving complements. A union, its complement, is the universal set, and there is no element in A intersection A complement. Now, like I said before, I do not expect you to memorize all the properties, but I expect you to be able to prove all the identities. And the proofs are very straightforward. Now, in proving the identities, there are a couple of different ways of doing that. Number one is to prove that each side of the identity is a subset of the other, and we would call that set inclusion. So we prove that A is a subset of B using set inclusion, and I'll show you an example after this. Number two is to use set builder notation and propositional logic to prove the properties. And number three is to use membership tables. Membership tables would be just like truth tables. You verify that elements in the same combination of sets always either belong or do not belong to the same side of the identity. Use 1 to indicate that it is in the set and 0 to indicate that it is not in the set. I'll show you an example, and it's very similar to the concept of truth tables. So let's look at De Morgan's laws. Number one, let's prove that A intersection B complement equals A complement union B complement. And then we'll try proving A union B, all of that complement equals A complement intersection B complement. So let's go ahead and do the proof. So let me restate the problem. Prove or disprove A intersection B prime equals A prime union B prime. Well, we are going to prove. So proof. This is the forward inclusion. We would prove that A intersection B prime is a subset of A prime union B prime. Then, of course, we're going to prove the reverse inclusion, which would be A prime union B prime is a subset of A intersection B, all of that prime. Then we would conclude that equality holds. Remember? Two sets are equal if and only if they are subsets of each other. So let's start with the forward direction. How do I prove that A intersection B, all of that prime, is a subset of A prime union B prime? I pick an element from the left-hand side and prove that it is in the right-hand side. Okay, that is how we demonstrated that A was a subset of B. A is a subset of B if every element in A is also an element in B. And to prove that, I pick an element in A and show that the element is in B. So let X be an element in the left-hand side, A intersection B prime. Required to prove X is an element of A prime union B prime. Now, let's proceed. But X, an element of A intersection B prime, what does that mean? You don't skip a step, you don't cheat, you use definitions, axioms, proven theorems, some other identities you already know until you arrive at the conclusion. And the conclusion has to be that X is an element of A prime union B prime. So X an element of A intersection B prime. What does this mean by definition? It means X is not an element of A intersection B. Now we use interpretation. What does it mean for X not to be an element of the intersection of A and B? It means X must be absent from at least one of them. That's very important because there's a little twist right here. If X is not in the intersection of A and B, it means X has to be absent. So this is A, that is B, that is A intersection B right there. If X is not in this intersection right here, it means X is either missing from A or not and, or X is missing from B. Why is it not and? Because it's possible that X could be in A, but X is not in A intersection B. Or X could be in B, but X is not in A intersection B. So if X is not in A intersection B, it implies that X is not in A or X is not in B. Okay? This doesn't translate as and, it translates as or. Now don't get confused with X an element of A intersection B. If X is an element of A intersection B, it means that X is in A and X is in B. But this time around, we're looking at X not an element of A intersection B. That does not translate as X is not an element of A and X is not an element of B. No, that would be a wrong translation. It translates as X is not an element of A or X is not an element of B. But what does it mean for X not to be an element of A? It means X is an element of A prime. Or what does it mean for X not to be an element of B? It means X is an element of B prime. But wait a minute. X is in A prime or X is in B prime. What does that mean by the definition of union? Mathematicians swear by definition. If you hear that there is a mathematician up there at the soccer field swearing, it simply means that guy is quoting definitions and standing on definitions. That is how mathematicians swear. They swear by definitions and nothing else. So that implies X is an element of A prime union B prime. Wait a minute. We picked X from A intersection B, all of that prime. And now we have X in A prime union B prime. So that implies where X came from, A intersection B prime, is a subset of where X is. A prime union B prime. This proves the forward direction, and we can smile a little because we're half done, and this gives us a good idea of what the reverse direction would look like. So let's go ahead and tackle the reverse direction. We now prove the reverse inclusion. You see, I put my little reverse inclusion here. And the reverse inclusion would be A prime union B prime is a subset of A intersection B, all of that prime. So I pick an element, let X be an element of A prime union B prime, and my desire required to prove X is an element of A intersection B, all of that prime. But X an element of A prime union B prime, what does that mean? It means X is an element of A prime or X is an element of B prime. Again, I'm using my definition of union. Mathematicians swear by definition. But what does that mean? By definition, again, if X is in A prime, that means X is not in A, or if X is in B prime, what does that mean? X is not in B. So if X is not in A or X is not in B, what is the obvious conclusion? X cannot be in the intersection of A and B. That means X has to be in A intersection B prime. Again, I'm just using my definitions. Every single step requires the use of a definition. You don't just fabricate steps. You go from one step to the other by definition. Okay, so our X came from A prime union B prime, and now we are at A intersection B, all of that prime. So we conclude that A prime union B prime is a subset of A intersection B, all of that prime, and this proves the reverse inclusion, and hence we're done. Try this. Prove or disprove. Of course, it's going to be proof because that's De Morgan's laws. Of course, it's going to be proved because that is De Morgan's second law A union B, all of that prime equals A prime intersection B prime. Just follow the exact same strategy we used up here and come up with a beautiful proof. We'll leave that as a simple exercise for serious students. Again, this is the textbook way of analyzing the proof. I'll leave that for you to study. And this is everything I've done, but I personally prefer my method. Okay, if we were using the set builder notation, it would be the exact same thing, except that this time around, I'm going to start with the left-hand side and go to the right-hand side, only using the set builder notation. So A intersection B is the set of all x in the universal set such that x is not in A intersection B, which means, and I follow this with my rules of logic to arrive at a conclusion. And then we have the membership table, like I mentioned before. It's simply the same as the truth tables we dealt with when dealing with logic. If I were to prove that A union B intersection C equals A union B intersection A union C using membership tables, you can see this is just like our true, 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 false, true, and so on and so forth. These are all the possible options. There are 8 of them, and I end up with these columns. So I look at these 2 columns, A union B intersection C, that's the column right there. I look at this column right here, and that's the column. These 2 columns match. Therefore, I can conclude that equality holds. But in this class, we are not going to use membership tables. We would use mostly set inclusion. So I pick an element X from the left-hand side and show that it is in the right-hand side. And I pick an element from the right-hand side and show it is in the left-hand side. And then conclude that since both sets are subsets of each other, equality holds. So go ahead and try this using set inclusion. And lastly, let's talk about generalized unions and intersections. So far, we've done A intersection B and A union B. Is that all? What if I had 3 sets? A intersection B intersection C, or A union B union C? Well, if I use this notation, union I from 1 to n AI, that simply means A1 union A2 union AN, and intersection I from 1 to n AI simply means A1 intersection A2 intersection AN. These are well defined since union and intersection are associative. So it doesn't matter if I were to do A1 and A2 first, and then take the union of that with A3, or if I were to do AN and AN minus 1 first, everything is well defined. So union and intersection, and this is a little example here for you. If I were to define my AI to be I plus 1, I plus 2, right up to infinity, then I can look at union I from 1 to n AI, which is just 1, 2, 3 up to infinity, or intersection I from 1 to n, which is just my AN, and there will be plenty of other examples we would look at in class. This brings us to the end of section 2.2, set operations, and in section 2.3 we'll look at functions. Then we'll touch a little bit into sequences and summations, cardinalities of sets, and maybe matrices. And from that point on, we would pick and choose a few more things to cover in this class, because the semester would have gone pretty well by then. So we may want to cover a little bit of counting principles, the pigeonhole principles in permutations, combinations, the fundamental counting rule, and so on and so forth. So you stay on and let's keep enjoying the class together. Thank you. God bless you, and bye-bye.